Okay, so welcome everyone to BilTop topology seminar. So it's great pleasure to have Henry Adams today. He's from Colorado State University, although he's on sabbatical leave at this point at ISTA. And so he's going to tell us about Vietoris-Rips complexes. So please take it away.
Thanks so much, Sian, and I'd like to thank all of the organizers for the opportunity to share. So I'll be speaking on Vietoris-Rips complexes, and certainly the entire first half of my talk is meant to be introductory. So please stop me with any questions as we go, and maybe I'll go a little faster in the second half of the talk, but there's no need, and the more you interrupt me, the better. So let me just start by advertising AATRN, which stands for the Applied Algebraic Topology Research Network. It's an online community, where we have regular talks. We now have 3,500 subscribers on YouTube, which is pretty cool, and about 24 hours watched per day on YouTube. So the web page is there, and check it out, and you can join our emailing list if you haven't yet and are interested. And if you have talks to suggest either by yourself or one of your students or a colleague, please reach out. All right, so let me describe Vietoris-Rips complexes. They're a way to turn a metric into a simplified. So X will be our metric space throughout this talk. And usually when you use the Vietoris-Rips complex construction to turn a metric space into a simplicial complex, you choose a scale parameter. Okay. So the vertex set of the simplicial complex is every point in our metric space. So here on the left is a metric space with, 12 points. And every point in this metric space is now just a vertex in our simplicial complex. Okay, and maybe I have the planar metric on this set of points. Then you have a finite simplex included in your simplicial complex when the diameter of that simplex is at most your scale. And the diameter of a simplex is just the length of the longest edge. So maybe I choose my scale parameter to be, approximately 1 inch. Then I have all these edges in my simplicial complex. Okay, I don't, for example, have this edge because that's too long. Maybe that edge was 2 inches. Okay, and then in the Vietoris-Rips construction, whenever you have all of the edges of a simplex, you fill in the simplex. So whenever I have all 3 edges of a triangle, I fill it in. Whenever I have all 2 edges of a tetrahedron, I glue it in, etc. So there's our Vietoris-Rips simplicial complex for that particular metric space and for this choice of scale, 1 inch. You'll notice as I increase the scale, I get more simplicities. A perspective that folks recently, including myself, have looked at is what happens when you build a Vietoris-Rips complex, not necessarily on a finite space or a discrete space, but maybe a continuous space, such as this circle here, this manifold. Okay, so it gets a little bit more complicated because let's say I still, have my scale parameter 1 inch. Not only do I have all edges of length at most 1 inch, right? But I have simplices of arbitrarily high dimension because I could fit 1 million points on the circle all within 1 inch of each other, right? And therefore I have a simplex on 1 million vertices. So when you build a Rips complex on top of something like a manifold, immediately once the scale becomes positive, you get an infinite dimensional simplicial complex, which maybe you don't have too much intuition about, but you can still handle and describe and study. Questions so far before I describe the history a bit? Vietoris invented these for use in cohomology theory. So we already had simplicial cohomology theories for simplicial complexes, but we wanted cohomology theories for other spaces, more general topological spaces, metric spaces maybe. So this is a way to build a cohomology theory for metric spaces. You sort of do this Vietoris-Rips construction, turn your metric space into a simplicial complex, and then Vietoris is taking the limit as the scale R goes to 0. Rips use these in geometric group theory. Rips, is instead sort of looking at scales that are large or even tending to infinity. Rips proved, for example, that if you have a group equipped with the word metric, so you choose a generating set and build the Cayley graph, and then you look at the shortest path distance in the Cayley graph. If that group is delta hyperbolic, then the Rips complex is contractible for all scales, at least 4 times delta. And he used this to produce finite Eilenberg-MacLane spaces, finite dimensional Eilenberg-MacLane spaces. A more modern perspective or recent perspective is coming from applied topology, which is my field of training. And there, Vietoris-Rips complexes are used to approximate the shape of a data set. So here, maybe I have a data set on 12 points, and I want to know what's its shape. Well, the Vietoris-Rips complex is a way to thicken the data set to sort of estimate the shape of the true underlying set space from which you might have been sampling those data points. And I'll talk more about this.
Henry, can I ask you a question?
Yes, please do.
Are you going to say more about this continuous circle example with infinite to many points?
Yeah, sadly, this is one of the few things that I like to talk about. so you'll have to try to get me to stop talking about this.
Okay, I will wait, but it's a curious example. So
yeah. So let me give one applied example that I think is quite nice. The cyclooctane molecule is a very pretty molecule in chemistry. It has 8 carbons in a ring, and then each carbon has 2 hydrogens sticking off of it. Okay, so the bond lengths are fixed, and the bond angles between adjacent carbons are fixed, but still there's degrees of freedom. Okay, so still the molecule can go in different configurations. There's a chair configuration and a boat configuration, things like this. Okay, so you can ask, what's the space of all possible configurations? Okay, so you can sample different configurations. Each configuration is a point in this picture, and this is just a PCA embedding of the data set of configurations down to 3D. Okay, the authors of this paper, they invented a triangulation technique to triangulate this data set, which is hard. An easier perspective is just take this data set and build a Vietoris-Rips complex on top of it. As you do that, you produce these things called persistent homology barcodes that track the topology of the space as the scale changes. So at small scales, you just have connected components, and that's represented by these 0-dimensional persistence bars. There's actually a lot more 0-dimensional bars that I've drawn here, but every data point will give you a 0-dimensional connected component. But eventually the Rips complex merges up into a single connected thing. As the Rips complex is growing larger and larger, you might get these small little holes that persist for a while, measured in 1-dimensional homology, but eventually things sort of stabilize and you just have one single 1-dimensional hole. And at small scales, there's no 2-dimensional homology until you thicken it up enough, and it turns out you get 2 2-dimensional features. So in this range of scales, there's sort of a consistent homology profile, a single connected component, a single 1-dimensional hole, and then 2 2-dimensional holes. Turns out this space, this conformation space of this molecule, is a sphere, which you can see, with a Klein bottle glued inside. So this hourglass that you see here is actually a Klein bottle. The Klein bottle is attached to the sphere along 2 circles of singularity. And when you glue a Klein bottle to a sphere in this way, you end up producing this homology profile. You actually end up killing the torsion of the Klein bottle. So it's a beautiful space. It's not a manifold, but it's a stratified space. It arises naturally in nature from this molecule. And from a finite sampling, you can sort of produce the homology groups of the space using Vietoris-Rips complexes, which might lead you to conjecture, a model for the space. Questions about this example? Okay.
So yeah, I have a question. So is there always a single region that is stable in the sense you described, or are there other, can there be multiple regions that give you different topologies, but they are still stable?
There can definitely be multiple regions. So a classic example here is pretend your data set is sampled from a coil, a knot, wrapping around a torus. Okay, so you have like 1 million points sampled on this knot wrapping quite densely around a torus. Okay, like it's 1,000,001 torus knot. Okay, so at small scales, you just have 1 million points, right? And then at slightly larger scales, you recover S1 because you recover this curve, right? But then at a next larger scale, you recover the entire torus.
Oh, okay, so for example, in this example, you're also regarding the first region where only there are points as stable topological space.
In this example, I would say there's only one sort of stable topology. Yeah, I mean, depends whether you want to interpret this as stable or not. But yeah, most people would say this is just sort of artifacts of noise, sampling noise. And then here you're recovering the homology of the true underlying space. But the example of this torus knot is sort of saying in some case there's no right notion of what is the true underlying space. It sort of depends on your how much you are blurring your vision.
Okay.
I also have a question, but how do you get the data points out of this molecule? Like, is it where it was, like tracing where you see the molecule, or how do you get these data points from the molecule?
Yeah, so there's actually a paper about this, not this paper, but referenced within, and shoot me an email, I can say more. This is a synthetic data set. So they actually use algebraic geometry to sample these configurations. The point being that the way you can build this data set is we have only focus on the carbons. So we have 8 carbons, meaning 8 x coordinates, 8 y coordinates, and 8 z coordinates. But then we have constraints, and they're degree 2 constraints. And the constraints are saying that all these bond lengths are fixed. And then to fix this angle, that's the same as fixing the length between not adjacent carbons, but second nearest neighbors. So you have this algebraic variety carved out by these constraints. All of these closest distances are 1, and all of these second closest distances are also fixed constant. And so they built a sampling technique to sample from this algebraic variety. They even took care in sampling from the singular circles.
Thanks. Yeah.
So a classic theorem in applied topology is the stability of persistent homology, which says, in black here, I have a manifold. It's a 2-hole torus. And in purple, I have a nearby data set, as sampling with all these purple points. Okay. These 2 metric spaces, the manifold and the sampling, are close. They're close in the Gromov-Hausdorff distance, to be technical. But the stability property says if I have 2 metric spaces that are close, then the persistent homology that I produce from their Vietoris-Rips complexes is also close. Okay. So what might the one-dimensional persistent homology of the Rips complex of this manifold look like? Well, it's a 2-hole torus. So I have four one-dimensional holes, right? These bars. And maybe, this hole fills in first and this hole fills in first. So that's why these bars die first. And these holes are a little bit bigger. So maybe they last for longer before things fill in. Okay. And now when I do this construction on the data set sampling X, right? So now you can really think of the Rips complex as building all these edges and triangles, right? It's something computable. You could store this one on your computer. Well, you might get some noisy bars, but the global structure of the barcodes are quite similar, okay? So nearby metric spaces give you nearby barcodes. And we want that in data analysis, right? We want, you want to have the property that as you sample more and more points, you converge to the persistent homology of your underlying space. Okay, let me skip this for now. Maybe we'll come back to it. I'll go to the question, which is, can you say more about the Rips complexes of manifolds or Rips complexes of circles? So I want to describe the Rips complex of the circle. And the perspective would be that in applications, people are building Rips complexes of data sets all the time, okay? As you sample more and more data points, that's converging to Rips complexes of manifolds, okay? But not much is known about Rips complexes of manifolds from a mathematical point of view. We know that at small scales, you recover the correct homology, right? So at small scales, you get the homology of the manifold, as we've done here. But we don't have a great understanding of what are the other artifacts that can come up at larger scales when you build Rips complexes, even on top of manifolds. So this happens in the circle. When you build Rips complexes on top of the circle, originally you recover the circle up to homotopy type, but then things fill in, at which point you might think it becomes contractible, but it doesn't immediately become contractible. There's a range of scales for which the Rips complex of the circle gives you the 3-sphere, and then the 5-sphere, and then the 7-sphere for shorter and shorter intervals of scale, until finally you reach the diameter of the circle, after which everything is contractible. Okay, so let me describe this a little bit. Our circle has the geodesic metric, so the distance all the way around is 2 pi. And so the diameter of the circle is pi. So once I reach pi, at that point, I'm going to have every possible edge. So I'm going to have the full simplex on all of the vertices of the circle. So I'm going to get something contractible. These are just the parameters where the homotopy type changes, okay? So they're listed here. 2 pi over 3, 4 pi over 5, 6 pi over 7, 8 pi over 9. Those are the scales where the homotopy type changes. Let me try to describe why. So we start with our circle and we build the Rips complex. And at small scales, you're adding in all these edges, all these triangles, all these tetrahedra. You immediately get something that's infinite dimensional as soon as your scale parameters is positive. But just think of it as a thick, infinite dimensional solid torus, solid annulus, right? That deformation retracts down onto this one-dimensional circle, okay? So it's got much, much thicker. It's become infinite dimensional, but it's still a circle up to homotopy type. Until scale 2 pi over 3. So 2 pi over 3 is 1/3 of the way around the circle of circumference 2 pi. So at that scale, the important change is that equilateral triangles appear, right? Because the diameter of this equilateral triangle is, this is just 1/3 of the way around the circle. The diameter is just 1/3 of the way around the circle. Okay. So you might think that when this triangle fills in, everything becomes contractible, but it doesn't, because you're not just gluing on a single triangle, you're gluing on a circle's worth of equilateral triangles. So not only do we have this red equilateral triangle, we also have a nearby green equilateral triangle, and we have a nearby purple equilateral triangle, etc. An entire circle's worth of equilateral triangles, in fact. Okay, so once I glue in all of these equilateral triangles, the new shape that I get is the 3-sphere. And let me describe why. Prior to scale 2π/3, I had all of these short edges, these small tetrahedra, etc. And I told you to think of this as an infinite dimensional solid torus. Put it right there in 3D in front of you. Just think of it as a 3-dimensional solid torus. Okay. Then I glue on one equilateral triangle. Think of this as gluing on a single disk. Okay. And then I glue on a second equilateral triangle. Think of that as gluing on a second disk nearby to the first one. And then I glue on a third equilateral triangle. And think of that as gluing on another nearby disk. Okay. And so what I have is I've started with the solid torus and I've attached a circle's worth of disks. Okay. So what I've built is I've built the genus 1 decomposition of the 3-sphere. I've written the 3-sphere as a union of 2 solid tori. Okay. One of the solid tori was just coming from the blue simplices, and the other solid tori was the circle's worth of equilateral triangles. So that's not how the first proof went, but that's the best intuition for where this 3 spheres coming from. Questions on that?
Can I ask you a question?
Mm-hmm.
Can we, instead of using all the points on the circle, can we take some sample points with, I don't know, and look for the density of the sample points so that we get the same results? Because
that's right.
Yeah.
That's exactly how our first proof went. We studied finite samples from the circle, equally spaced samples, extremely carefully. And we proved that once you reach a certain, fix a scale parameter and then add more and more points. We proved once you reach a certain density of points, the homotopy type doesn't change. Let me just say
So you first fix a scale parameter. That was my also other concern. So when you talked about stability, since you are, so you assume that the scale parameter changes continuously, right? You are not choosing some sample scale parameters and then look at the corresponding Vietoris-Rips complexes.
Two different concepts, I would say. So the stability concept, you have 2 nearby metric spaces. You prove that their persistent homology barcodes as Rips complexes are close. And this is a statement that you need to sort of consider multiple scales at once.
So when you write this, first I thought that you are going to choose some R values, the scale parameter values, and then consider what you have and then calculate the first homology groups.
Are you talking about this slide, the Rips complex of the circle, or the stability slide?
In both, okay, let's look at the circle. And
yeah.
Okay.
So this was just an offhand comment that the first way these homotopy types were proven was, let's look now just at one scale at a time, like this scale. We want to prove that the Rips complex of the circle at this particular scale is a 3-sphere. Okay. We proved that once you have a dense enough finite sample on the circle, sampling more points doesn't change the homotopy type. So that was just related to your question. I can tell you the fewest number of points you need to see this 3-sphere. The fewest number of points you need is 8 points. Because when I have 8 points, the scale is such that I have all possible edges except antipodal edges. Okay, so I have all edges of step 1 around the circle. I have all edges of step 2 around the circle. And I have all edges of 3 steps around the circle. Okay. And so what's important here is what I'm missing. I'm missing these antipodal edges. Okay. So with 8 points at scale 2 pi over 3, those are the only things I'm missing. And what I actually have here is the boundary of a cross polytope on 8 vertices. So on 2 vertices, the cross polytope in 1D space is an edge, and its boundary is the 0 sphere. And then on 4 vertices, the cross polytope in 2D space is a diamond, and its boundary is a circle. And then on 6 vertices, in 3D space, the cross polytope is a 3D ball, but its boundary is an octahedron. Maybe you could see the octahedron there, right? So the cross polytope in 3D has an octahedral boundary. So you could obtain this as a Rips complex of 6 points on the circle, this 2-sphere. Okay. And then on 8 vertices, that's the fewest number of vertices you need to get this 3-sphere. It's a boundary of the cross polytope in 4-dimensional space. But I sort of keep going off on tangents. More questions.
In the torus decomposition, in the first decomposition you mentioned, how many equilateral triangles are we gluing? Or all of them, or just as how many?
All of them. Yeah.
Oh, okay.
You need to glue in all of the equilateral triangles to get the 3-sphere. Because in blue, think of this solid torus as the simplices I had prior to scale 2 pi over 3.
Mm-hmm.
And then in the colors, red, green, and purple, think of each disk, this red disk, this green disk, this purple disk. Each disk is an equilateral triangle. And I need the entire circle's worth of equilateral triangles
okay.
to get this second solid torus here.
Oh, I see. Okay.
Yeah.
How did you realize this S3 when the scale parameter is between 2 pi over 3? Did you calculate the third homology, or?
How did we prove it?
Yes, that it is S3.
That's right. So the sketch of the proof is as follows. First we proved the homotopy type of any evenly spaced finite sample of points from the circle, the Rips complex thereof. Okay. So for any sample of points on the circle, finite sample, the Rips complex always has a homotopy type, which is either an odd sphere or a wedge of even spheres, it turns out. Okay.
Oh, okay.
And then we understood the induced maps on homotopy type when you either increase the number of points or when you increase the scale. Okay, so we understood those induced maps as you increase the number of points. Increasing the number of points is more relevant here. Then we observed that the Rips complex of the entire circle is the union of Rips complexes of finite points on the circle, right? So consider all Rips complexes of any finite set, take their union, you get the Rips complex of the entire circle. Just because any simplex only has a finite number of vertices, right? So if a simplex appears in the Rips complex of the entire circle, it appears in the Rips complex of some finite subset of the circle. And then we use properties of colimits and homotopy colimits. Okay, so this Rips complex of the entire circle is the union of the Rips complexes of all finite subsets, but these are cofibrations because they're just inclusions of simplicial complexes. And so we could use properties of homotopy colimits. And one lemma that we proved is that fix a scale parameter. Once you have enough points, sampling more points doesn't change the homotopy type, right? So in this large diagram of Rips complexes of finite subsets, we prove that the homotopy type stabilizes. Right? It stabilizes, say, at the 3-sphere for this choice of scale. And then since all sufficiently dense finite subsets, their Rips complexes have the homotopy type of the 3-sphere at that scale, that means by the property of homotopy colimits, that so does the Rips complex of the entire circle. it's a very combinatorial proof. And some of the things I might talk about are motivated by the desire to have a more geometric proof. Good question. Yeah. Other questions?
So what you proved is the homotopy type of these simplicial complexes that you obtain. But these, so yeah, okay, thank you very much.
Yeah, that's right. Yeah, these are these infinite dimensional simplicial complexes. And we prove their homotopy types. All right, let me use this to segue to the next topic that I don't need to discuss in detail, but I'll give you at least the idea of. I'm using Rips complexes with the less than or equal to convention here, which means it's simplex is included if its diameter is less than or equal to r. Okay. People also, myself included, we also studied the less than convention. Okay. So I explained a little bit these odd sphere homotopy types that appear in these intervals, right? So you take a circle, glue on a circle's worth of equilateral triangles, and you get the three sphere. From this three sphere, if you glue on a circle's worth of four simplices, you get the five sphere. From this five sphere, if you glue on a circle's worth of six simplices, you get the seven sphere, etc. With these infinite dimensional simplicial complexes, something very undesirable happens right at this critical scale. So right at this critical scale, you actually get an infinite wedge of two spheres. Okay. And that all these critical scales. Okay, so it only happens for a single scale, but it's sort of ugly in some sense. Actually, this happened at scale 0. At scale 0, what we had with the less than or equal to convention is we had an infinite wedge of 0 spheres. Sorry, my pen's not working. Right, because at scale 0, when I build the Rips complex at scale 0, I have every point on the circle as a vertex, but I have no edges in my simplicial complex. So I just have an uncountable number of vertices. I've sort of destroyed the topology on the circle when I build this Rips complex. Okay. I need to then thicken the Rips complex. I need to increase the scale to recover the circle.
Is this
again.
like changing the topology as this parameter changes?
Yeah. I'm not changing the topology as the parameter changes. I'm adding more simplices to the Rips complex.
Oh.
Yeah. So, but what's going on here is if I take a manifold, it has an obvious map into the Rips complex of the manifold, but that map is not continuous. Okay. Because the manifold has some sort of continuous topology, but in the simplicial complex, the vertex set always has the discrete topology, right? Every vertex is in an open set containing no other vertices, right? Whereas not every point in a manifold is in an open set containing no other points, right? So this is a very bizarre topology in some sense. That's what gives us this infinite wedge of two spheres, right? When we glue on the circles worth of equilateral triangles. Because in the simplicial complex topology, the barycenter of the red equilateral triangle is not close to the barycenter of the purple equilateral triangle. So when I glue on these disks, it's like there's space between these nearby disks, okay? And that's creating one of my two spheres, this space between these disks. I actually have an infinite number of two spheres, right? But it's really just the wrong topology, quote unquote, wrong topology in some sense. I mean, the fact that this inclusion is not continuous is telling you that this space in some sense has an undesirable topology. So one thing that I've studied is putting a better topology on this space. And with the better topology, you get the three sphere homotopy type immediately right at this scale. So with this better topology, the equilateral triangles are glued together with the right topology immediately. You don't have to wait for things to be filled in by tetrahedra, sort of. So maybe I'll briefly describe this topology now. So X is a metric space. Our scale parameters is R. We're going to build the Vietoris-Rips metric thickening. That's what it's called, the space within the topology. But in order to describe it, first I'm just going to define the geometric realization of the Vietoris-Rips complex. Okay. We've already seen the Vietoris-Rips simplicial complex. It's just all simplices of diameter at most R. So what's its geometric realization? You include all simplices of diameter at most R. And then you take convex combinations of those simplices. And that sort of fills in edges or fills in triangles. Okay. So the geometric realization is just convex combinations of vertex sets that formed a simplex that had a sufficiently small diameter. To put a new topology on this, I'm going to call it a metric thickening. The superscript M just stands for metric. And the perspective is I don't take convex combinations of points. I take convex combinations of direct delta masses. Okay. So a convex combination of direct delta masses is just a probability measure. It's a probability measure, with diameter, whose support has diameter at most R. So let's say X is this manifold and I build this metric thickening. In the Rips simplicial complex, I might have had a triangle here and I might have had a point in its geometric realization. But now I think of that point at the barycenter as just a measure with mass 1/3 at each of the vertices. Okay. So this point in the geometric realization of the Rips complex, I now interpret as a measure, probability measure, with mass given by the barycentric coordinates. And similarly, in my Rips complex, if the scale is large enough, I might have had this tetrahedron in the Rips complex. And maybe I have some point in barycentric coordinates inside this tetrahedron. In this new perspective, I just reinterpret that as a measure whose mass at each vertex is given by the barycentric coordinates. And now I can put a new metric on the space, the optimal transport metric. So the distance between these 2 points, this blue point and the red point, is just sort of the work I need to pay to transport, the blue pile of dirt to the red pile of dirt. So that would be the best transport plan, and I pay a cost associated with this transport plan. And that tells you the distance between these two measures. So it's sort of like if I perturb the vertices of a measure just a little bit, then that's a continuous change in the topology. And the reason why this is beneficial for us is going back to this picture now. Let me change slides. Going back to this example on the circle, with the new metric, and this should be 2 pi over 3. With this new metric at scale 2 pi over 3, I get the 3-sphere immediately, okay? And the point being, I might have one equilateral triangle in red. I might have a nearby equilateral triangle in purple. Consider their barycenters. So their barycenters are when I have mass 1/3 at each of these points, or the barycenter of the purple triangle. Think of that as the measure with mass 1/3 at each of these points. Those masses corresponding to the barycenters are now very close in the optimal transport distance, because just a small perturbation, a small amount of work, moves the red pile of dirt onto the purple pile of dirt. So that's why, at this new metric, we sort of get the 3-sphere right away. And I should say, with this new metric, the inclusion from the underlying space, say a manifold, into the metric thickening, that's continuous now, and it's an isometry onto its image. So this topology is quite nice and for a lot of purposes. Questions?
When r is equal to 0, what do you get with the new metric?
With the new metric, yeah, when r is equal to 0, take any metric space X. This is just equal to X and isometrically.
Okay.
Because all you've done is you've taken your metric space X and you've recast it as each point is now just a Dirac delta measure. And then the optimal transport distance between two Dirac delta measures was just the original distance between the points. So, yeah, I mean, it's a really nice metric. Both perspectives are useful, the simplicial complex perspective and this new metric. For years, we didn't really understand the relationship between them, though, so well. Recently, however, we've proven that they always give the same persistence diagrams, so long as you ignore whether an endpoint is open or closed, right? So with the Vietoris-Rips simplicial complex, maybe some endpoint is open. And then if I move to the metric thickening, maybe that endpoint of a barcode fills in. But that's the only possible difference between the barcodes. So yeah, the Rips simplicial complex and the Rips metric thickening, they have the same barcodes. With the less than or equal to convention, they might have different homotopy types, right? Because, you know, with the Rips simplicial complex right here, we had an infinite wedge of 2 spheres, whereas for the metric thickening, we just cut the 3 sphere. A good conjecture is that if you use less than convention, there's homotopy, but it seems tough to prove. And yeah. More questions? Maybe I'll keep going for about 15, no, 5 more, no, yeah, I guess 15 more minutes with time for questions at the end. Does that sound good? Okay.
Yeah.
One nice thing about this new metric is that we can say the first new thing about Vietoris-Rips thickenings of n spheres. Okay, so what happens is the following. Okay. So I have an n sphere and I build the Rips complexes of it, and I ask what are the new homotopy types that come up. Okay. So I'm typically going to talk about the 2 sphere right now. The first change in homotopy type of the 2 sphere is when this equilateral tetrahedron appears, this inscribed equilateral tetrahedron. Okay. And I'll let R2 be the diameter of that tetrahedron. Okay. So more generally, you have an n sphere. The first change in homotopy type is when this inscribed n+1 simplex appears, and I'll let Rn be the diameter of that simplex. Prior to that equilateral tetrahedron filling into the 2 sphere, you know, you maintain the 2 sphere homotopy type. We're able to say the first new homotopy type that comes up, it's a join. It's a join of the original space joined with the parameter space of tetrahedra we glued in. And this actually happened in the case of the circle. You know, the first new homotopy type of the circle was the 3 sphere, but think of that as the circle joined the circle. The original circle, the space we started with, joined the parameter space of triangles that we glued in. We glued in a circle's worth of triangles. Okay. So maybe I won't go through the proof sketch, but that's the important point here. First new homotopy type often seems to be join, the join of the space you started with, and then joined with the parameter space of the critical synthesis you glue in. I mean, what is all this notation? This describes the number of equilateral regular tetrahedra I glue in, because SO3 is all the rotations of this tetrahedron. This allows me to rotate from any tetrahedron to any other. But A4 is the rotational symmetries of this tetrahedron. Okay. People have very little understanding of the later homotopy types. I mean, I would guess that it's not contractible until you reach the diameter of the sphere, which is later. And I would guess that the homotopy conductivity goes to infinity, you know, just like it did with the circle, but we don't have a good understanding there, but we really need it. Let me touch on some implications of these homotopy types of circles and spheres, unless there's a question.
I have a question.
Yeah.
What happens with n equals 2? So what is SO3 over A4?
Yeah, so
homotopy type or the...
So let's look at n equals 2. Yeah, this is great. We talk about this a little bit in our paper. This paper is joint with, it's called Metric Reconstruction via Optimal Transport. It's the paper where we introduce this metric. And it's with Michael Adamaszek and Florian Frick. So n equals 2, we get S2 joined SO3 mod A4. You could also write this as S3 mod, some people call it like E6 or something, or some people call it 2T, like the binary tetrahedral group or something. So correct me if I'm wrong, so I don't make mistakes on YouTube, but S3 is a double cover of SO3, I believe. And that allows you to understand the fundamental group of the space, right? And so, you know, for example, we can describe the homology of S2 joined SO3 mod A4. You know, this just joining with the sphere just shifts the homology up with some dimensions, okay? The fundamental group of this space, using the fact that S3 is a double cover, is Z mod 3Z, okay? So then I bump up the dimension because I'm joining with this 2 sphere. And so I get that this is Z mod 3Z if I is equal to 4, I believe. And then Z if I is equal to 6. So we have a remark along these lines in our paper. Michael Katz is a student of Gromov's, and he sort of studied this homotopy type that comes up in a very different context. He was studying the filling radius of Riemannian manifolds, and so in the definition of the filling radius, when you apply that definition to the 2 sphere, that's how this space came up for him. Recently, Memoli, Lim, and Okutan sort of proved that those spaces are homotopy equivalent to the Vietoris-Rips complexes. Yeah, so we were able to sort of generalize some of Katz's work to now work for any sphere, which is cool. And I'll just say another perspective. I mean,
so they will always appear as orbit spaces of actions on spheres, and is it a coincidence that it's an orbit space of S3 with the action of binary tetrahedral group, or is it something you will expect that's always an orbit space?
No, yeah, I would expect to see joins in orbit spaces as you get the later and later homotopy types. Yeah, but yeah, we're missing the theory here. I mean, really, we need a Morse theory that works in this context, and we need a Morse spot theory because of all the symmetries involved. Let me say something that's targeted at some of the members of this audience, I believe. Okay, so let's go back to the case of the circle. I sort of tried to motivate that you should think of this first 3 spheres S1 join S1, but maybe you should think of it as S1 join S1 mod Z mod 3Z. Right? I mean, that is just a circle, but Z mod 3Z is the rotational symmetries of this equilateral triangle, right? And then
You mean
This-
S1 mod, Z mod 2, maybe? You had A2 before, the A3. I see Z mod 3.
Yeah, it's just the rotational symmetries of the equilateral triangle. There's 3 rotational symmetries. You know, down here, this was mod A4 because, you know, the alternating group on 4 vertices is the rotational symmetries of the tetrahedron. But come back to this S5. You should think of this as S1 join S1 mod Z mod 3Z join S1 mod Z mod 5Z, I think. So that's just a circle, and that's just a circle. So the threefold join of circles is indeed the 5-sphere, okay? But I've written these other circles in this way to sort of describe the fixed points, right? There's some extra fixed points when I rotate this equilateral triangle by 3, or this regular 4 simplex when I rotate it 1/5 of the way around, okay? So you can ask, I have a circle action on this Rips complex. What's the equivariant cohomology? I mean, this is a question I just asked recently with this polymath group I'm on. And these Rips complexes are infinite dimensional objects, but this is probably the right finite dimensional model. And the circle acts on this, right? And you should be able to, you know, sort of understand the equivariant cohomology. And also as the scale grows, right? As the scale grows in the Rips complex, you keep adding more and more terms. So I think that's a cool question. Let me just say one last connection, and then I'll pause with time for questions. Well, there's connections to Borsuk-Ulam theorems. So folks have studied Borsuk-Ulam theorems in the lower dimensional space. We can actually give versions of the Borsuk-Ulam theorem into higher dimensional space. And the basic idea is just in the proof. You know, circle maps into higher dimensional space. Well, you can along the Rips complex. So then you get a map from this Rips complex into higher dimensional space. Well, the Rips complex, you know, is an odd dimensional sphere. So you can now apply the classic Borsuk-Ulam theorem on this, you know, map from a high dimensional sphere into high dimensional Euclidean space. And then what does it say? I mean, certainly when you include a circle in the higher dimensional space, antipodal things don't collide. But we find sets of bounded diameter whose convex holes collide with their antipodes. Okay, and we can prove sharpness of these bounds. And if we had more understanding of, you know, Rips complexes of spheres, we could prove Borsuk-Ulam theorems for maps from spheres into higher and higher dimensional spaces. One last connection that I'll advertise is to, oh, I'm over time, I apologize, is to Gromov-Hausdorff distances. So what are the Gromov-Hausdorff distances between spheres? Lim, Amoli, and Smith recently proved some nice results. We recognized their entries in this distance matrix of Gromov-Hausdorff distances between spheres as scale parameters where Rips complexes change homotopy types. And so now just recently we're able to prove new things about Gromov-Hausdorff distances between spheres. You know, we prove lower bounds on Gromov-Hausdorff distances between spheres using the topology of Rips complexes and ideas related to Borsuk-Ulam theorem. So let me stop there. Thanks so much for your time and attention and all of the great questions.
Okay, thank you very much, Henry. Any questions? Any further questions?
What is a Gromov-Hausdorff distance? Could you briefly say?
Yeah, definitely. Okay. One complete definition is written here, but I'll give you a different definition. Okay. So first I'll describe the Hausdorff distance. Okay. Oh, sorry, I'm zooming out so you can't see. Okay. So X and Y are metric spaces, and pretend they're embedded first into a common metric space. So here the common metric space might be the plane. Okay. The Hausdorff distance is how much, what's the smallest epsilon such that when I thicken x by epsilon, I contain y. And when I thicken y by epsilon, I contain x. Okay, so when I thicken y by epsilon, I get something like this. And I ask what's the smallest epsilon so that I contain the curve x. Okay. And when I thicken x by epsilon, the curve, I get something like this, and ask what's the smallest epsilon such that I contain y. Okay. So that's the Hausdorff distance. X and y are two metric spaces. They're embedded into a common space, here the plane. And how much do I need to thicken? What's the smallest epsilon so that one metric space is epsilon thickening contains the other? The Gromov-Hausdorff distance, x and y no longer need to be embedded in the same space. So I infimize over all spaces Z that emit isometric embeddings from x and y, and I infimize over all possible isometric embeddings. And then once I've embedded x and y into Z, I just look at the Hausdorff distance in Z. So it's the nearness of metric spaces. It's used in theoretical contexts like Riemannian geometry sometimes. It's used in applied contexts like matchings between spaces. You know, a lot of Gromov-Hausdorff distance is hard to compute, but a lot of things that computer scientists do compute are inspired by the Gromov-Hausdorff distance. But the theoretical properties are poorly understood. So Facundo Momoli and his group has been working on this for a long time. You know, what are the Gromov-Hausdorff distances between spheres, these classic metric spaces? And they were able to prove some bounds. And then, you know, we recognize some of these entries. And in particular, you know, like the distance between the circle and the two-sphere is the same as the distance between the circle and the three-sphere, right? And that's somehow related to the fact that when you build the Rips complex of the circle, when you thicken it enough by 2 pi over 3, not only does it emit an odd map from the two-sphere, but at that same scale, it now also emits an odd map from the three-sphere. So,
did they find R2, the second line?
yeah, so Lim, Molly, and Smith have proven these distances exactly, both lower bounds and upper bounds.
So
they
nothing
also
happens until 2 pi over 3 for S2.
What's that?
So for example, for S2, the homotopy type does not change until 2 pi over 3. Should we read it like this?
Yeah, you're sort of talking about this slide, right?
Yes. Yes.
The homotopy type of the Rips complex of the two-sphere doesn't change until R2. R2 is not 2 pi over 3. R2 is the diameter of this inscribed tetrahedron inside the two-sphere.
Okay. Okay.
R1 is 2 pi over 3.
Yes.
Yeah. Yeah. So you're right. I mean, so this is the picture I would draw for when you build the Rips complex on the two-sphere. The homotopy type doesn't change until you reach R2, the diameter of this inscribed tetrahedron, right? This table is meant to denote something different. The Gromov-Hausdorff distance is a notion of distance between metric spaces. Here I'm drawing this table of distances between all the spheres, okay? So this table is supposed to denote the Gromov-Hausdorff distance between the two-sphere and the three-sphere, and then the Gromov-Hausdorff distance between the two-sphere and the four-sphere, and the Gromov-Hausdorff distance between the two-sphere and the five-sphere. I mean, it's a symmetric matrix, right? But if you blur your vision, you know, it's almost like, hey, these were all the scale parameters where the Rips complex of the circle changed, right? And these were the known scale parameters so far where the Rips complexes of these higher spheres change. And that connection is sort of illuminated by this theorem. You know, so far it's only a lower bound, how the topology of these Rips complexes controls the Gromov-Hausdorff distances. But I don't think it's unreasonable to conjecture that, you know, it'd be beautiful if this was an equality. So I might conjecture that, but there's no evidence in the opposite direction yet.
Is it possible to even conjecture that if they have two spaces have Gromov-Hausdorff distance, say D, then Vietoris-Rips complex bigger than D, they have the same Vietoris-Rips complexes, or some, like when they have close for the Gromov-Hausdorff distance, their Vietoris-Rips complexes should be somehow close. Is that possible? Or
I mean, in some sense, that's
theorems are just something similar. But
I mean, in some sense, that's the stability of persistent homology. Remember those stability slides, right? So, some sense.
But I think what you showed for S1 says that the answer should be no, because S1 behaves like S2, then it starts to behave like S3. So it is not always S2. Yes.
So let me make this stability bound more precise. So there's a notion of distance between persistent homology called the bottleneck distance. It's a notion of distance between the barcodes, okay? So if I have two metric spaces, M and X, the bottleneck distance between the persistent homology of the Rips complexes, I'll just put a dot here. Okay, so I look at the persistent homology of the Rips complex of M, I look at the persistent homology of the Rips complex of X, and the distance between those persistent homology barcodes is bounded by at most twice the Gromov-Hausdorff distance between M and X, okay? So what's quite interesting is that this gives bounds on the table of distances between spheres, right? It gives lower bounds. But those lower bounds are off by a factor of 2, okay? So those lower bounds that you get easily by stability are like by a factor of 2 worse than this bound, okay? So the idea that was really introduced here is that equivariance is from the Borsuk-Ulam theorem, as do we. So somehow you also need equivariance to get these tighter lower bounds here. So, I mean, I think Rips complexes and Gromov-Hausdorff distances are very, very closely related. And we're only now starting to understand the precise relationships between them and how to make those relationships tighter.
Okay, any other questions? Okay, so if not, let's take Henry for the great talk. Thank you very much.
Thanks so much. Yeah, thanks for all the great questions. I'd be happy to chat any more, anybody, so let me know.